Dear students, today we are going to discuss the topic sp3 hybridization in alkanes. So we will first get introduced to, we will first go through the atomic number of carbon, we will draw the electronic configuration, and then we will slowly get introduced to the concept of hybridization, and then we will see what is the tetrahedral angle and the tetrahedral shape. Let us start. sp3 hybridization. What is the smallest alkane? Yes, methane. The atomic number of carbon is 6. The electronic configuration of this carbon is 1s2, 2s2, 2p1x, 2p1y and 2pz0. At first it will seem that the valency of carbon is 2. See, if here one electrons come, it will become fully filled orbital. If here one electron comes, it will become fully filled orbital. So the carbon would become stable. So at first glance it would seem that the valency of carbon is 2. But if the valency of carbon is 2, then a molecule like methane won't exist. We all know that methane exists, and this indicates that the valency, this molecule indicates that the valency of carbon is indeed 4. So what happens here? Actually, before carbon interacts, combines with hydrogen, carbon goes into an activated state. When it goes into the activated state, the electron from the s orbital, it jumps to 2pz orbital. So now I am going to draw the electronic configuration of the activated carbon atom, which is 1s2, 2s1, 2p1x, 2p1y and 2pz1. Now it is clear that the valency of carbon is 4. It is very clear. Now we can combine 4 hydrogen atoms. Okay, we will try to combine the 4 hydrogen atoms here. Hydrogen atom, what is the atomic number? 1. What is the electronic configuration? Yes, 1s1. The spheric S is a spherical shaped orbital. So I am going to draw a sphere. That's it. 1s1. So I am going to draw 4 1s1s here and try to combine it with these orbitals. Okay, 1s1, 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 1s1. This is one electron, this is one electron. It forms a covalent bond, covalent bond, covalent bond, covalent bond. So now 4 covalent bonds are formed, and now it would seem that the CH4 molecule is formed, but it is not the case. Can you find the odd one out of these? Yes, you are right. These 3 are same. This is sp, this is sp overlap, this is again sp overlap. This is the only odd one out. This is an ss overlap which is occurring. The ss overlap means that it is a head-on overlap. When the overlap is head-on, it means that the bond energy is greater. That is, the energy required to dissociate this bond or to break this bond is greater. Okay, so the bond energy released will be greater in one of the bonds if one of the bond is broken, and the bond energy would be lesser if 3 of the bonds are breaker, and these would be equal. If such is the case, do such a case exist? We know the structure of methane. It's like this. Is this the case that if one of the bond, if it is broken, more energy is released? No. Here the concept of hybridization sets in. So now we will discuss the concept of hybridization. What actually happens? How energies become equal? We will discuss. We have the board. So I am going to draw the activated carbon electronic configuration one more time on the board. 1s2, 2s1, 2p1x, 2p1y and 2pz1. These are the 4 atomic orbitals. The 4 atomic orbitals are of different size, different shape and different energy. The 4 atomic orbitals now mix and merge with each other to form 4 new sp3 hybrid orbitals. 4 sp3 hybrid orbitals. What has mixed? 1s and 3p, they have mixed together to form 4 new sp3 hybrid orbitals. I am going to draw the 4 sp3 hybrid orbitals. Notice that it is made up of 1s and 3p. So the 4 new orbitals are having 1/4 character of s and 3/4 character of p, or you can say 75% of p character and 25% of s character. This can be much better understood if you observe the lobe. The lobe is now broader in shape because now it contains a part of s. Here the lobe was a more lobe shaped. So now here it is coming broader in shape. So this is because 1s has been added. Dear students, the case is similar when we prepare tea in a kitchen. When we mix the ingredients, we are using different ingredients: water, milk, sugar and tea powder. All are having different energy, different flavor. But when they are mixed together, and when we pour the cup of the tea on 4 cups of tea, on 4 cups, each cup is similar. Each cup is similar in flavor. Each cup is similar in energy. So this concept is hybridization. This is very similar to the concept of hybridization. Okay, let's get back. The 4 new hybrid orbitals are already formed. I am going to draw the 4 new hybrid orbitals of carbon. Here 1, 2, 3, 4. What do you think? Whether it will remain like this? Never. Each orbital is having 1 electron. They are like charges, they are negative charges, they will repel each other. We have already studied VSEPR theory in preliminary classes. In VSEPR theory, according to VSEPR theory, the orbitals will go to the farthest position possible in space. Farthest position possible in space. When there are 2 orbitals, the farthest position is the linear position, 180 degree. That is the farthest position. When there are 3 orbitals, the trigonal shape is the farthest position. When there are 4 orbitals, the tetrahedral shape is the farthest position available. It is at this position that repulsions are minimum. Let us draw the farthest position possible for all orbitals. This is the farthest position available. 2 of the orbitals are protruding towards you. One is protruding away from you and one is up. So this is the farthest position that is available. Now the carbon, our carbon atom is ready. It can now make covalent bonds with hydrogen. So I am going to make covalent bonds with hydrogen here. Each orbital is attacked by 1s1 orbital of the hydrogen, and now we get the methane molecule. Can you observe the shape? Right, it is the tetrahedral shape. Tetrahedral shape. And can you observe the angle? Yes, the angle between any 2 bonds. Between any 2 bonds is 109 degree 28 minutes. This is the optimum angle. Optimum angle. That is, it is at this angle that the groups are at the farthest position available. If the angle deviates, then again the repulsion forces sets in. So this is for methane. This is for methane. The tetrahedral shape, the tetrahedral angle, it is at this shape and at this angle that the groups are at the farthest position and they are stable. This is for methane. We can draw, you want to know for ethane? It's very simple. I'll show the tetrahedral shape and the tetrahedral angle in ethane also. This was methane. You want to go for ethane? Remove one hydrogen, place one carbon. Ethane. The angle between any two bonds is 109 degree 28 minutes. You want to go for propane? It's simple. Write one C. Propane. The angle between any two bonds is 109 degree 28 minutes. Each of the carbon atom in alkane is sp3 hybridized. Each is having a tetrahedral shape and each is having an angle of 109 degree 28 minutes. Thank you.